Have you ever really thought about the power in your home? I mean, the electricity from a battery might give you a tiny little zap, but the stuff from your wall socket, well, it's a whole different ballgame. It turns out they are two completely different kinds of electricity.
So, we've got two main players in the world of electricity. First up is direct current, or DC. Think of it like a one-way street. The juice flows steadily in one direction, from positive to negative. Simple, right? That's your batteries. But then there's alternating current, or AC. This is the stuff that powers our homes, and it's a current that is, well, it's constantly changing its mind.
So why does it do that? Why not just stick with the simple one-way flow of DC? The answer is actually pretty cool. It's not about chemistry, like in a battery. It's all about pure physics. And it all begins with something incredibly simple, spinning a magnet.
And that brings us to this fundamental rule of the universe called Faraday's law of induction. Now, it sounds fancy, but the idea is beautiful in its simplicity. If you have a magnetic field around a wire and you change it, you create or induce a current in that wire. The key word there, the most important word, is change. No change, no current.
This is basically the heart of every single power plant. You take some force, wind, flowing water, steam, doesn't matter, and you use it to spin a coil of wire inside a magnetic field. Because it's spinning, the magnetic field it experiences is constantly changing. And that continuous change is exactly what creates a current that flows one way and then back again.
Now, you might think all this spinning would create some kind of chaotic, messy current, but it doesn't. That smooth, predictable rotation creates a perfect, predictable rhythm. The physical motion of that spinning coil gets translated directly into the electrical signature of the current. It creates a very specific shape. And that signature shape is the famous sine wave. You could say this wave is the very personality of AC. The height of the wave tells you its strength, and whether it's above or below the center line tells you which direction it's flowing. As you can see, both of those things are always in motion, rising to a peak, dropping to zero, reversing, and doing it all over again. So how do we even see this? Well, we don't. Get this. The electrons in the filament of a light bulb are actually stopping and reversing course 100 or 120 times every single second. It's flickering like crazy, but it's happening so incredibly fast, our brains literally can't process it. Our persistence of vision just blends it all together into a steady, constant glow.
So for every single push forward, that's what we call the positive half cycle, there's an equal and opposite pull backward, the negative half cycle. The two halves are perfectly symmetrical. It's a perfect push followed by a perfect pull. And this leads to a really interesting question. A paradox, almost. If the current pushes forward with a force of, say, +1, and then pulls backward with a force of -1, over one complete cycle, doesn't that all just cancel out? Isn't the average flow of electrons just zero?
Yeah, think about that for a second. If the net flow of electricity is zero, how on earth is it powering your TV right now? And maybe the most important question of all, if you're not technically getting any net electricity delivered, why in the world does the power company get to send you a bill every month? Okay, so here's the secret. The whole time we've been thinking about this the wrong way. Power isn't about the direction the electrons are flowing. It's about the energy that flow delivers. You see, when electrons move through a wire any direction, they create friction, and that friction generates heat. That is where the actual work gets done.
And here's the little bit of mathematical magic that makes it all work. The amount of energy delivered, that heat, is proportional to the square of the current. And what happens when you square a negative number? It becomes positive. So it doesn't matter if the current is +1 or -1. When you square it, you get a positive result. The direction becomes completely irrelevant to the amount of power being delivered. This clever calculation is what engineers call the root mean square, or RMS value. It's really just a way to figure out the effective power of AC. It answers a simple question. What DC voltage would I need to produce the exact same amount of heat? The RMS value is the true measure of what AC can actually do. So, when you look at an appliance and you see a number like 220 volts or 120 volts in some places, you're not looking at the average voltage, because that's zero. And you're not even looking at its peak voltage. You are looking at the RMS value, the effective power.
And this is where it gets a little bit wild.
For a circuit with that RMS value of 220 volts, the voltage is actually swinging all the way up to a peak of around 311 volts in the positive direction, and down to negative 311 volts. That's way higher. And that right there is why AC is generally considered more dangerous than DC of the same rated voltage. Its peak is almost 40% higher.
Okay, so we've cracked the code on how to measure the power of this weird, wobbly current. But that's just the beginning. When you start building actual circuits with this stuff, a whole new level of cool, complex stuff starts to happen.
Probably the best way to picture what happens next is to imagine the voltage in the current is two dancers, and they're both moving to the rhythm of that AC sine wave.
Now, in a super simple circuit, let's say with just a basic resistor, like a heating element, our two dancers are in perfect harmony. They're totally synchronized. When the voltage hits its peak, the current hits its peak. When one is at zero, so is the other. They are perfectly in phase.
But what happens when we make the circuit more complex? When we add things like motors or computer chips? What happens when one of our dancers starts to lead the other, hitting its peak just a fraction of a second early? And what does it mean for the whole circuit when the other dancer starts to lag behind? Well, that is a whole other dance, and a story for another explainer.